I'm going to get the exams back to you today. But going through the exams, I see that, this pace is hard to keep up with, probably 6.5 hours per day. And then, I'm not sure how many people are doing the homework. The homework is, to review your notes, but probably not that many. One thing you have to be aware of, in Chem 1A, there's not nearly as many hours like in the class, and so they don't have enough time to go through much. So, and the problems, they don't have that much time to go through problems either, just because there's a lot of material to cover, and the questions are, a step up. They're significantly, can be significantly harder. Some of the questions are the same, but it's going to be harder, and so be aware of that. And you don't want to, you don't want to fall, if you're planning to continue in chemistry, like Chem 1A, Chem 1B, maybe organic, you don't want to fall too far behind. It's really hard to catch up. And so anyway, we'll continue here talking about this. I'm not sure how effective this is, going through these problems. If you don't have time to go back through them, we go through these, but it's like watching, some video of some performance, let's say piano or something, once, and then if you don't go through it over and over again, it doesn't register, doesn't stick. And so you have to, even though we go through these problems, I'm expecting you guys to go through them as well as going back through your notes repeatedly. And so you can build a good foundation for Chem 1A. But if you just go through it once and it never clicks and you don't remember any of it, it's going to mean Chem 1A is going to be pretty tough, or, subsequent classes. And so watch out for that. Now's the time to catch up. Although, tomorrow's the last day, so it's a little late, but still, they're take-home exams. Anyway, let's continue with the problems here. State the effect of a temperature increase and a temperature decrease on the rate of chemical reaction. So increase, reaction speeds up, more collisions. Decrease, fewer collisions. Not only more collisions, but the collisions are more energetic. And so collisions are more frequent and more energetic. Suppose that two substances are brought together under conditions that cause them to react and reach equilibrium. Suppose that in another vessel, the same substance and a catalyst are brought together, and again, equilibrium is reached. How are the processes like? How are they different? It's the same reaction. The only difference is one, you're using catalyst, the other you're not. It's the same reaction if we only look at the reactants and products. If we look at the path, the progress, the mechanism of the reaction, it's different. With the catalyst, the mechanism is different. It's like, when we combust methane, we just look at methane and oxygen initially, and then CO2 and water at the end, but there's a whole bunch that happens in between, the flame, etc. And so that whole bunch that happens in between is the realm of kinetics. Kinetics is, biologists are very interested in kinetics. The reason biologists are very interested in kinetics is because kinetics gives clues as to the mechanism. And biologists are very interested in the mechanism of drugs, and there's a whole mechanism of disease, this kind of stuff. So a lot of biologists are really experts at kinetics and all this type of stuff, transition states, enzymes, etc. That's where I did most of the kinetics, was in biochemistry, as a matter of fact. But anyway, the equilibria are identical. That's just, reactants and products. Equilibrium will be reached more quickly in the system with a catalyst because it provides a lower energy path. You don't have this steep of a hill to climb. This is catalyst. Automobile catalysts used to be very expensive because they contain platinum. They no longer contain platinum. They could use other metals, a lot less expensive. And so the one-time thefts of catalysts used to be very common. Not so much anymore because cheaper catalysts have been found. For the hypothetical reaction A plus B yields C, what will happen to the reaction rate if the concentration of A is increased? If concentration of A is increased, then we get more collisions, you know, higher concentration, more collisions. Oh, and the concentration of B is decreased. Well, if B decreases, then we're going to get fewer collisions. And so we have to know what the dependence on A is and what the dependence on B is. You can't tell just because it's 1-to-1. You can't tell because the overall stoichiometry isn't what happens in the mechanism. We have to understand the mechanism in here. This is why it gives a lot of clues, because the people who study these things, which I didn't really study much mechanistic stuff, the people who are really into this mechanism stuff, they'll adjust the A concentration, see how that impacts it, and adjust the B in concentration, see how that impacts the rate. You know, and that gives you clues, you know, how B is used and A is used and how they react and how they collide, this kind of stuff. And so people are very interested in that. In fact, for combustion of methane, it wasn't really well understood. I mean, combustion of methane's been around for centuries, but it really wasn't well understood mechanistically. Yeah, obviously they understood the product, CO2 and water. That's been known for like a century, but how, you know, how do you get from methane and O2 to CO2 and water? That's the tricky stuff. So it wasn't until maybe about 25 or 50 years ago that somebody figured out all the steps involved. And there's something like 2,000 or more than 2,000 steps, you know, involved with a number of intermediates. And so a whole bunch of different ways that things are all connected with one another. An increase in the concentration will increase the rate, while decrease in the concentration B will decrease. The net effect depends on the size of the two changes. Not only the size, but the mechanism. You know, it's not just the size. For example, you could have a small change in B, but it could have a larger impact than a large change in A because of the mechanism. So people are really after the mechanism and the transition states. You know, how does it transition from one state to another? There's a transition state. And so this is why people use Spartan, you know, Spartan to analyze different hypothetical transition states. You know. When will the reverse reaction, okay, let's see, in nitrogen and hydrogen brought together. So this is the Haber reaction. At the proper temperature and pressure, they will react. This reaction normally doesn't happen. It has to be under really set of conditions that wasn't so easy to find. The set of conditions was determined empirically, I think, by Haber. Empirically meaning just try a whole bunch of different temperatures and a whole bunch of different pressures. But we could analyze this. You know, this looks like it would be more favorable at higher pressure. It should be more favorable at higher pressure because on the left here, this should be a plus. That's not a 1, it's a typo. On the left here, we have a total of 4 moles of gas. On the right here, we have 2 moles of gas. So higher pressure should favor the side with fewer moles of gas over here because higher pressure is usually smaller volume. There's one way we can make higher pressure. Now, there's another way to make higher pressure. We could add like inert gases here, but the inert gases isn't going to have any impact on this. So we can increase the total pressure by adding some inert gas, but it's going to have no impact here. So it's, when I talk about higher pressure, I'm talking about these gases here. In temperature, well, it depends. Is this exothermic or endothermic? You know, that's going to dictate it. The temperature. We can oftentimes we can estimate it based on stability, which side's more stable, you know. But nitrogen itself is quite stable. This one is kind of hard for me to estimate. 21, when will the reverse reaction rate be at a maximum? At the start of the reaction, after equilibrium has been reached, or at some point in between? After equilibrium is reached, because that's when you're going to have the maximum, you know. What's going to happen is you're going to build up the maximum concentration of ammonia. And then as the more ammonia you get, the more reverse reaction you have. And so when that reverse reaction is equal to the forward reaction, then there's no more net change. And what that means is that you can't get any more ammonia. You know, that's the max. And so that'll be the max reverse rate at equilibrium. On a single set of coordinate axes, sketch graphs of the forward rate, reaction rate versus time, and the reverse reaction rate versus time from the moment the reactants are mixed, the establishment of equilibrium. So here, you know, if we plot on the y-axis, let's say concentration, the square brackets means concentration of the reactants. The reactant concentrations are going to decrease. You know, as they react, we're going to get fewer of them. As we get fewer of them, there are going to be fewer collisions. So the reactants are going to decrease. Okay, the products start off at 0 because there's no products initially. And so this will be 0. And then as the reaction takes place, we'll start to build up the concentration of the products. As the concentration of the products increases, eventually it's going to meet here with the reactant concentration. And it's going to stabilize here once equilibrium is established. And so the product concentration is going to build up until there's so much product that the reverse reaction is occurring at the same rate as the forward reaction. So it's going to look something like that. So, you know, the situation is, you know, a graph like this, a lot of people won't remember this, you know. So there are certain tricks I always did in trying to remember figures and graphs. Figures and graphs, I always drew those in my notes. Figures and graphs, I'd write myself a little annotation. And in the annotation, I'd have it like the take home. You know, this is the take home message. And the take-home message is easier for me to remember because it's in my own words. I'd never memorize something like this, and I'd never write something like this verbatim. You know, if I read something like this, then I'd rewrite it in my own words down here. And then that helps me remember it. And then also the repetition. If you actually go through your notes more than once, and I know some people, they'll never go through their notes, no matter, you know, no matter what. You know, they could be so much more successful in classes like this. But for some reason, there's some kind of activation barrier that, you know, prevents them from capitalizing on that potential success. And those are the I call them. But, you know, as you go on, like I said, things get harder and harder, and so you don't want to be in that position. So, you know, what you do is you have this, so you have some annotations, and then you see it. Like if you saw this 10 times, it's easy to remember, you know, and it's easy to see it 10 times because it's just 10 days worth of review. Yeah. But, you know, you do the homework. So I do the same thing with the homework. You know, a lot of people will do the homework once and then that's it. What I do is I review all these problems. I have it, you know, the homework notebook. I have actually 2 separate notebooks. I had a lecture notebook and a homework notebook. And so I keep all the homework in the same place. And I do the same thing with the homework. I just flip through and look at it, you know. And that's also because I have bad memory too, but you know, that helps me remember things, you know. And it's not memorization. This is not memorization, you know. This is like, think of this as building your scientific vocabulary, you know. If you're learning a language and you have no vocabulary, it's going to be extremely hard to speak that language. And so you're building your vocabulary here, but it's just more than vocabulary. Well, actually vocabulary is a lot because you can do a lot with words, but these are going to be like tools that you're building, you know, tools, problem-solving tools. And so a lot of people will think, that's just memorization. No, not at all, because once you have those points of memory, then the work of your brain is to make all those connections. And I think somebody, I don't remember this because I didn't review it and I didn't write it down, but I was watching one talk, and they're talking about this, like 1 point of memory has like, once all the connections are established, it could have like one neuron has like 10,000 connections. Well, it was something like 1,000 or 10,000 connections. This was a talk I went to at UCLA last year, actually. And it was a talk about neurons. And this is very interesting. They built this, at UCLA, they built this little chamber in which they could hear the neurons communicate with other neurons. And they played it, and they played it, and the person said it was real time. And what they found out was that the neurons communicate much faster with each other than what they had originally thought. This guy's kind of interesting. The professor that was head of this project was a physicist, not a biologist. And it was pretty interesting. The reason I went there is because my memory's bad, and so I was thinking of ways to improve the memory. But it was pretty interesting because at that talk they were talking about, so you develop one memory neuron, something like that, but it takes time to build up all those connections. So this is helping you build all those connections, is by this is my hypothesis, is by doing this review. A lot of people don't believe in my hypothesis. A lot of people say that, if just looking at the answer is not effective. I disagree with that, And so I think here you're building up that neural network that's so important in problem solving. But that's if you're interested in that thing, and you could hear it because he played the neurons communicating. It's like a song, and it's not like, it's really weird. There's patterns to it, and so I don't know if they've analyzed the patterns and the frequencies. It's like little clicks, and I think it's online. So I think he has recordings of actual neurons communicating with one another, just electrical signals. Pretty interesting. Anyway. 25, if the system 2SO2 plus O2 yields 2SO3, so sulfur dioxide, oxygen, this is a redox reaction, or oxidizing sulfur dioxide to sulfur trioxide, is at equilibrium and the concentration of oxygen is reduced. So if this is at equilibrium, then we have this the right ratio, product to reactant ratio, and it's stable. But if we screw up that ratio by removing oxygen, then we aren't going to have the right product to reactant ratio. So what's going to happen is going to shift. This is Le Chatelier's. And so we expect to shift to the left. And so more sulfur trioxide will decompose to compensate for it. And a new equilibrium will be established. The new equilibrium won't be exactly the same, but it'll have exactly the same ratio. Equilibrium will shift in the reverse direction. More O2 will be produced, reestablishing the ratio. But the amounts and amounts and concentrations and pressures will be different. But they just have to multiply and divide to the same ratio. If additional oxygen is pumped into the system, so here, this is another redox. This is burning ammonia. And if we burn ammonia and oxygen, we can form some NO gas. In which direction will the reaction shift? So if we pump more oxygen in there, it's going to burn it more efficiently. So it's going to shift it to the right, shift forward to the right. And then it's going to reestablish an equilibrium. This is probably not 100% burnt. Maybe the driving force isn't as big. And so the equilibrium, there might be some unburnt residual ammonia left over. And it's hard to burn under these conditions unless you increase the oxygen. In Chem 1B, you do these types of calculations all the time. You figure out how much unburnt ammonia would be left over, based on empirically, the ratio here, product to reactant, is usually determined empirically from experiment. That's our target ratio. So we can figure out how much I'm burnt. And we can get something called the percentage reaction, something like this. Predict the direction of the shift for the equilibrium here. Okay, this is Lewis acid-base reaction. You know, copper 2 is a Lewis acid and ammonia is a Lewis base. And then what it forms is this. This is a weird ion called tetraamine copper 2 ion, which is very deep blue. You know, it's this color of blue here. This is copper 2 in water. This is the tetraamine copper 2. It's an ion. And so this is a, you know, clear because you can see through it. It's not a precipitate. And it's a dark blue, so deep blue, clear deep blue solution. They can mix it. This isn't well mixed. They mix it. They just dumped in a whole bunch of ammonia on the top here. So if we reduce it, if we reduce the concentration of ammonia here, then we're going to have less of the deep blue color because this equilibrium will shift to the right. And so if we decrease the ammonia concentration, we'll revert to light blue. This is light blue here, copper 2 aqueous. This is deep blue here. We can shift it either way. We add ammonia, we shift it to the left. We reduce ammonia, we shift it to the right. You know, we can add copper, we'll shift it to the left. Reduce copper, shift to the right. So shift to the right is forward. A container holding the equilibrium, so we have hydrogen and CS2 yields methane and H2S. This is a redox reaction here in this case. This is kind of a weird redox reaction here. Because the oxidation states, you know, normally when we do the oxidation states here, you know, hydrogen's 0 because it's elemental form. Here, carbon disulfide, we'd expect -2 for each sulfur, giving a +4 for the carbon. And then over here, you know, hydrogen's +1 in a compound, and that means carbon's at -4 here. And then over here, hydrogen's +1 and sulfur is -2. So it looks like as if nothing happened to the sulfur. And so this reaction looks like it's between the hydrogen in the element and carbon in CS2, carbon disulfide. And so it looks like the carbon disulfide gained electrons from hydrogen, 4 hydrogens. Actually, it needs to gain 8 electrons. You know, 4 electrons will take it to 0, and another 4 will take it to -4. So we need 8 hydrogens to do that, each hydrogen losing 1. Okay, if we increase the volume, it favors the side with more gas. And so over here, we have 4 moles of hydrogen gas, 1 mole of CS2 gas. On the right, we have 1 mole of methane gas and 2 moles of H2S gas. So altogether, we have 5 moles of gas on the left. And altogether, we have 3 moles of gas on the right. Now, gas takes up a lot of space. A liter of gas under normal conditions, that is room temperature in 1 atmosphere, is 24.5 liters. And so about 25 liters. And so this would be about 125 liters under normal conditions. This would be about 75 liters under normal conditions. And so if the container is enlarged, it's going to favor the side with more moles, so it shifts to the left. The other way of thinking about it is the concentrations are changed, you know, and they're not impacted equally unless, because numerator to denominator, they're not impacted equally. We aren't going to get into it in that much detail. Chem 1B. So shifts to the left. In what direction will carbon monoxide and water? This is called the water gas shift reaction. This is a very famous reaction. You know, carbon monoxide is a poison, but if you react it with steam, you can form carbon dioxide. However, we also form hydrogen gas, which is a good fuel. Carbon monoxide is not a great fuel because it doesn't have that many electrons. I mean, carbon's +2, it's going to +4. So it's not the best fuel. Hydrogen is a much better fuel. And so this is one way that people are proposing to make hydrogen, but still it's expensive, you know, because you're reacting with steam and you need carbon monoxide, a source of carbon monoxide. One source of carbon monoxide is from metal refining, you know, and a lot of metal refining processes, carbon monoxide is a byproduct. Well, this gives a good way to, carbon monoxide is not that valuable chemical compared to hydrogen. So this is a good way to convert carbon monoxide, which would have been waste, hazardous waste, to hydrogen, which could be used as a fuel. So the volume is going to shrink. If the volume shrinks, then we favor the side with fewer moles of gas. But looking at this reaction, we have 2 moles of gas on the left, because water is a gas. And this is a high temperature reaction. This is why it's expensive. High temperature reactions are expensive because you need all the heating equipment to do it, and you need a lot of energy to get the reaction to go. And we have 2 moles of gas on the right. So 2 moles of gas, 2 moles of gas, neither side's favored. Neither side's favored, there's no shift. And so we expect no shift. It will not shift because both sides have the same number of moles of gas. Which direction of the equilibrium 2NO2 yields N2O4 plus 59 kilojoules will be favored if the system is cooled? So if we cool it, we're removing heat. You know, cooling is removing heat. So if we remove the heat, heat is a product here. This is exothermic. It's going to favor the forward reaction here. Heat is removed, forward reactions preferred. If your purpose were to increase the yield of sulfur trioxide in the equilibrium, so here we have sulfur dioxide reacting with nitrogen dioxide to form sulfur trioxide, nitrogen monoxide or nitric oxide. Would you use the highest or lowest temperature possible? What do you guys think? If you want to make more product, would you increase the temperature or decrease the temperature for this reaction? Yeah, that's one of the things I was thinking is, you know, about 6.5 hours. 6.5 hours is pretty tough. And so this class may not have, at least the way it's designed, may not suit. Everybody, you know, it's a long time to have to keep concentration. Some people are, you know, some people are keeping up okay. Sure. But you know, some people could be doing better trying to keep up. And you know, for Chem 1A, you're definitely going to have to do a lot of work to just stay on top. Material problems are a lot harder. That's why. And so some of the problems are a lot harder. So anybody? Decrease the temperature? Yep, that's correct. That's good, Dana. Decrease the temperature, cool the system. The solubility of calcium hydroxide is low. It reaches about 2.4 times 10 to the minus 2 molar at saturation. The solubility has two definitions. One definition is it soluble or insoluble? That is, will it dissolve or not dissolve? That's qualitative. That's the solubility rules. Calcium hydroxide, we qualitatively said this: hydroxides are all insoluble except for group 1, ammonium, calcium, strontium, barium. And so we called calcium hydroxide soluble, but now they're saying the solubility of calcium hydroxide is low. These are the types of things, like, you know, if these are the types of things that some people will catch and most people will not catch it, you know, because it's because some people will have the little bit of information memorized and then see, you know, there's something weird. You know, this is like, you know, discovery of penicillin. The discovery of penicillin is something that wouldn't have been caught, you know, unless this person, you know, Pasteur, who discovered it, you know, had some, you know, basic knowledge memorized. And you see these things like, this would be a conflict, you know, they're saying the solubility is low, but wait a minute, didn't we say calcium hydroxide was one of the soluble ones? And so this gets people thinking at a deeper level. When it gets people thinking at a deeper level, they think, okay, what exactly is the definition of solubility? Well, the definition of solubility is something soluble if we can get more than, according to your solubility rules, if we can get more than 0.1 moles to dissolve in a liter. Now, that's our solubility. It reaches about 2.4. This is 0.024 moles per liter. 0.024 moles per liter is below our criterion. And so this needs a little asterisk. Calcium hydroxide would have a little asterisk here. Yeah. There's a region that's close, like silver sulfate. Silver sulfate's another example of one that's kind of borderline. You know, calcium hydroxide's borderline, but we threw it in the soluble camp. And so those are things that you don't pick up unless you have, you know, that kind of stuff, some stuff memorized. And so there is great value in memorizing some things. You know. There's also great value in repeating, you know. How you memorize things is you don't try to learn new things and memorize things. You just kind of memorize things that you know already. And that repetition helps, but it's like doing chemical reactions, you know, predicting chemical reactions. You know, if you do the same problem over and over again, like 10 times, you know, then you start to see things differently. Okay, anyway, in acid solutions with many H+ ions present, calcium hydroxide is quite soluble. Explain this fact in terms of Le Chatelier's principle. There are two ways to explain this. In terms of Le Chatelier's principle, if we're looking at solubility, then we have something called KSP. This is soluble in water. So if I have solid calcium hydroxide, what happens is it'll saturate the water solution. When it saturates it, the calcium ions break off and the hydroxide ions break off the surface of the crystal. And that's going to saturate it. And once I reach a certain concentration of calcium ions and hydroxide ions, then those are going to precipitate or recrystallize. And once the dissolution and the precipitation rate are equal, then we've reached the state of dynamic equilibrium where no more calcium hydroxide will dissolve. And so I'll put some calcium hydroxide here, but I'll have some excess calcium hydroxide solid, like that. And once the concentration of the ions increases to the point where they, they come back and stick at the same rate that they're breaking off, then we've saturated the solution. And the other definition of solubility is the maximum amount, of solute, calcium hydroxide, that I can dissolve in a given amount of solvent, water in this case. So what we can do is we can remove the hydroxide to get more to dissolve, or we can remove the calcium to get more to dissolve. Well, how are you going to remove the hydroxide? One way we can remove the hydroxide is by, well, hydroxide is a strong base. We can remove the hydroxide by adding acid. If we add acid here, the hydroxide and the H plus react. This is Arrhenius type reaction to form H2O liquid. Also Bronsted, also Lewis. And so this is how we're going to do it. We're going to reduce the hydroxide chemically by adding H plus to convert the hydroxide into water. Driving force for this would be stronger to weaker acid base. Driving force, the reactions are based on driving force. Metathesis, the driving force for metathesis or precipitation. You have to say precipitation, if a precipitate forms, or stronger to weaker acid, or gas formation. Those are the driving forces. A particular chemical, like, you might say, oh, the driving force is CO2, but the particular chemical is not necessarily, it's a process, what's happening with the CO2. Or a lot of people will say water is the driving force. Well, not really. I mean, water, you can get a glass of water that's going to drive what, It's the driving force is always relative to something. And driving forces for reaction going from less stable to more stable. That's the thermodynamic driving force. In Chem 1B, you'll learn that entropy disorder can have an impact on things as well. And so, but that's, that's beyond the scope of this class. That's for metathesis. For redox, we're going from stronger oxidizer, stronger reducer, to weaker oxidizer and weaker reducer. That's it. All redox reactions are the same. And then for acid base, is this stronger acid, stronger base to weaker acid, weaker base. This is a metathesis reaction. This is kind of the reverse of a metathesis reaction. If I take calcium ions and hydroxide ions, they like each other. So the driving force for this reaction is formation of the precipitate. So this reaction is favored to the left. If I looked at the K value for this, K is the ratio of product to reactant. It's very small, because we don't expect much of the ions. We expect mainly the precipitate. Now this is pure solid, so this gets a 1, in the equation. So, in fact, we could dissolve all the calcium hydroxide if we had enough H plus. It'll keep shifting this until it all dissolves. And so calcium hydroxide is soluble in acid. Write the equilibrium constant expression. So here, this is going to be the concentration of CO2 times the concentration of H2 divided by the concentration of CO. And this is a gas, so the concentration of H2O gas. And so K, which is the constant, this is the ratio that we should have at equilibrium. And so this is our target. So when we do calculations for the stoichiometry of this, we use this to figure out at the end, in the ICE table, what the stoichiometry yields, and then it often doesn't yield 100% reaction. Sometimes we'll have 99% reaction, sometimes we'll have 80%, sometimes 50%, sometimes 5%, sometimes 1%. It depends on this ratio, how much reaction we'll actually have. These ratios are determined empirically or theoretically. We can get these theoretically as well. 43. Okay, this is going to be the concentration of CO times the concentration of H2 divided by the concentration of H2O gas. Now carbon is a solid, so its concentration doesn't change. Let's say I had a pound of diamonds. If I have a half pound of diamonds, is it 50% carbon now? And 50, well, in other words, did the concentration change? No, concentration is still the same. It's still pure diamond, 100% diamond, 100% carbon. You just have half as much. And so concentration of pure solids and pure liquids do not change. So those are just given a 1. So in this particular case, we have the concentration of CO, concentration of H2, divided by 1, which they don't show, and divided by the concentration of H2O, which is here. And so this is, again, the product to reactant ratio that we're after. Here, this is going to be different because it's going to be concentration of Zn2 plus cubed, because we have a coefficient of 3. So we've got to cube that. And then we got to square the concentration of phosphate. But this is divided by zinc phosphate, which is a pure solid. Its concentration doesn't change, so that gets a 1. So it's zinc concentration cubed, phosphate concentration squared divided by 1. This one's going to be the concentration of hydronium times the concentration of nitrite divided by the concentration of nitrous acid. And H2O is a pure liquid. So if you drink a full glass and you drink half of it, it's not half as concentrated. You have half as much of pure water, or, you know, at least the same concentration of water you started with. And so that gets a 1 equation. So we don't see H2O, it's a pure liquid in this. It's a 1. Over here, this is the deep blue tetramine copper 2 ion, light blue. So in this one, we got the concentration of copper 2, concentration of ammonia to the 4th power divided by the concentration of copper. So the 4th. Over here. When we do the math, math can become quite hard. You know, solving 4th order equations can be hard. You know, solving quadratics is kind of hard too. You know. And so this is why I recommended the calculator. You know. So at least if you have a quadratic equation, it's a lot easier to do the math. Even a cubic equation, if you have a cubic equation, you can use that same calculator to do cubic. But when we have a 4th order equation like this, we can't use that calculator. And so we have to use other ways to solve this, the math in this. The math in this is going to allow us to figure out the stoichiometry of this equilibrium reaction, which is different than doing the stoichiometry, you know, you need to know the standard stoichiometry where we just assume it reacts to 100%, you know. And you need to be able to do limiting reagent and excess reagent type problems as well, because those are important for calculating, you know. Let's say you're going to try to make something. When you try to make something, then you want to keep one, the limiting, and the other, maybe slight excess, you know. The equilibrium between nitrogen monoxide, oxygen, and nitrogen dioxide may be expressed as the equation here. Write the equilibrium constant expression for this equation. So it's going to be the NO2 squared divided by NO squared O2, all concentrations here. We can also do this by pressure too, but which is beyond the scope of this class. We're not going to get into it. And then express the same equilibrium in at least 2 other ways. Write the equilibrium constant expression for each. The constants numerically equal. Cite some evidence to support your answer. I don't know what they're talking about. Express the same equilibrium in 2 other ways. One, I guess we could reverse this reaction. I'm not sure what they're talking about. And so here we have the NO2 squared, NO squared, O2, all concentrations. I guess they are talking about the reverse, but the reverse is, you know, the reverse reaction is like this. We just flip it. And so this is reactants, products, we flip it. Now NO2 will be the reactants, these will be the products. When we flip that, the equilibrium constant expression flips also. Here. Oh, I see what they're saying here. And so they're reversing this, then K is inverted, you know. Well, you're just changing the roles. So you got to flip K. And then what they're doing here is they're multiplying by coefficient. So they're doubling everything. If we double everything, then everything is squared here. So it's going to be 2 squared, which is 4. And then 2 squared is 4. And then 1 squared is just 2. Okay. And so this is multiplying by coefficient. The numbers aren't going to be different. Of course, the numbers are going to be different. You know, this is a different reaction you're looking at. Although this one's weird. If we double everything, you know, oh, they're cutting it in half. This one they're cutting in half. This one they're doubling. That's a little weird, but I wouldn't worry about it because, you know, this also happens in chemistry. You know, the first time you hear it, it might not click. You know, and that's because your brain hasn't developed the neural connections. And so normally I never worry. If the first time I hear it, it doesn't click, I don't worry about it. Because eventually it's going to click. And you just got to make sure it clicks before the test, you know. And so by that process of review, this is how I'm getting, you know, I leave a lot of problems on the side. Like when I was a student, I'd leave a lot of problems, I couldn't figure it out. And there was, let's say, no solutions guide, I can look it up. So I left it on the side and then I just let it sink and then think about it every day. And then eventually it'll click. For 47, why wasn't H2O used again for K? For 47, H2O was in the liquid state. You know, if this were gas, then we do it like here. The big difference is the liquid, and concentration of the liquid doesn't change. You know, and since the concentration of liquid, let's say we ate up half the H2O. So let's say we started off with 100 milliliters of H2O. And this is 100 milliliters of H2O. This is pure H2O. Pure H2O is actually 55.5 moles per liter. And so we call it like 55.5, around there, 55.5 molar, or 100%. And so we have 100 milliliters of 100% H2O. And let's say we consumed half of it. Now we have 50 milliliters. Is it going to be 50 milliliters of 50% H2O? Or is it going to be 50 milliliters of 100% H2O? In other words, did its concentration change? Is it still 100% or is it now 50%? Well, it's still 100% here. That's different than this problem above it. This problem above it has H2O in the gas phase here. And so the key difference is H2O is in the gas phase. And so if we have a box and the H2O is in this box, and this H2O is going to have some molarity, you know, let's say this is 1 liter box, and let's say that this is like 1 mole per liter, so 1 molar. Then if we consume half of it, we still have the 1 liter box, but we have half as many molecules. And so if we started off with 1 molar H2O gas here and we eat up half of it, we're going to end up at 0.5 molar. Say this is 1 molar. So we're going from 1 molar to 0.5 molar. Whereas in a pure liquid, you know, here, we went from 100 milliliters to 50 milliliters here. And so pure liquid doesn't change. The volume of the liquid is going to be dependent on how much liquid we have, not the volume of the container. The container might be a 1 liter container, but that's going to have no impact on the volume of the liquid. You know, if I have 100 milliliters of water in a 1 liter container, I ignore the 1 liter. I could use a 5 liter container. I could use a 100 milliliter container. You know. But for gases, the container does matter here. So the thing, you know, my little annotation I would write in my notes is this, you know, the take-home message: solids and liquids ignore in K. Then, you know, I read that over and over again, you know, ignore solids and liquids in K. I read that over again and over, and then eventually you get bored of reading this over again and you think, why? You know, why can I ignore solids and liquids? And then all that's going to take you to the next level. You know, there are different levels that you see, and you'll notice this in classmates. As you go on, you'll see fewer. But, you know, when you start off in beginning classes, there's some people that you may notice that, you know, struggle just to remember this. In fact, they can't. And then you got the people who will remember this, but that's all they can do. And then you got the people who remember this, and they remember this very well, and then start to think beyond. You know, memorization is just so you can get a step up to think at higher levels. You know, you step up to think to higher levels. And so here, you know, now we can start thinking at higher levels. You know, why solids and liquids, and then you can maybe come up with some visualizations for this you can propose. But the first part is just, you know, just to learn this. You don't have to step up to the higher level. You need to learn the basic, you know, first. And if you want to ignore any of the why part, or, you know, any of the deeper, you know, theoretical part of this, the deeper description, then at the very least, just memorize this. They'll save you. This is just strategies. So it's like, okay, if I don't really understand this, you know, it doesn't quite make sense, I don't worry about it. I just memorize this. And then when I go through my repetition, I figure eventually it's going to click, you know, eventually I'll figure it out. But at least I know this basic part right now. Some people get hung up, like if they don't understand it, they refuse to memorize it. It doesn't make any sense, because then you can't really do, you know, some of this stuff is extremely complex, and it takes, you know, a lot of work to just sort things out. And then you aren't going to progress. You're going to run into a dead end, which lots of people do. I mean, you know, I've seen it because I've taken tons of classes. And so like this, I don't worry about it. I just memorize this, and then later on, after going through repetition, then I start thinking, well, I'm kind of bored of this. I want to know more. You know, that's when, you know, you're ready to do it. So some things, you know, may not make sense initially, but give it time, because there is a lot of repetition in science too, and even in the classes. You know, some classes are more progressive than others. You know, what we're trying to do, this is why Chem 4 is a little bit harder than the book. Chem 4 is a little bit harder than the book because we want to make it more progressive. That is, we don't want a big, you know, what happens is people, if we just use the book, people go from Chem 4 to Chem 1A with unrealistic expectations, because it's kind of a step. The Chem 1A book we use is, which is Petrucci's, on the higher end of the spectrum. It's on the harder end. If you go to UCLA and take the general chemistry at UCLA, they use an honors level book, you know, university honors level book. University honors level book expects everyone to have calculus, expects everyone to, so when you compare, let's say, UCLA's standard chemistry book to our chemistry book is still high level, but it's not an honors level. And so what an honors level book, like at UCLA, will compress our first 5 chapters into 1 chapter. And so that's too much for us, you know, to take the first 5 chapters and compress it in 1 chapter. And so, but ours is still pretty challenging. You know, it's still on the harder end, and a lot of schools don't use it. So we try to make it progressive, you know, as far as the steps up. But it's a big step up. Petrucci has Pretty good book. If sodium cyanide solution is added to silver nitrate solution, the following equilibrium will be reached. Okay, so this is again a Lewis acid-base reaction. These Lewis acid-base reactions are very common. Here, cyanide attacks the silver ions. There's an electron pair donor and bonds to it. We form this. This has a funny name. You'll learn how to name these in Chem 1B, but this is called dicyanide argentate 1. That's kind of a weird name. But cyanide loves silver ions, it loves gold ions, loves those things. So in a lot of mining, they use cyanide to extract the precious metals like silver, gold. So cyanide pollution, cyanide contamination has been a problem. I think, I can't recall, but I think there's a big cyanide pit right before getting to the town of Mojave out in the desert. It used to be an open air, but I think they were forced to cover it because so the cyanide salts could blow out onto the highway 14 there. Cyanide's pretty toxic. But I think that was a silver mine out there. I'll have to look into it. It was so long ago. I remember that from a geology field trip. Okay, when I started off as a geology major. So I still like geology. All right, when we look at this equilibrium, it's 10 to the 18, which means it's all this. That means cyanide is excellent at extracting silver ions. Look at it, it's 10 to the 18 to 1. 10 to the 18 to 1. 10 to the 18. We can't say parts because, they're unequal parts. Like, for example, we have 3 parts reactant, but we'll just crudely say it's 10 to the 18 parts to 1. 10 to the 18 parts of product to 1 part of reactant. And so this is why cyanide's used. In a lot of mining extraction processes, it really captures all the silver ion out there. In which direction is equilibrium favored? Yeah, forward direction for sure. Look at that K, it's gigantic. K is very large. Favoring, K is the ratio of the products divided by the reactants. A certain equilibrium has a very small equilibrium constant. In which direction? Okay, it's very small. It favors the reactants. Reverse direction favors the reactants. In chapter 9, we discussed how to identify major and minor species and how to write net ionic equations. These skills are based on the solubility of ionic compounds, the strength of acids, and the stability of certain ion combinations. In other words, you ionize the strong electrolytes. What are the strong electrolytes? The strong electrolytes are the soluble salts. So you need solubility, of course, ionic compounds. The strong acids, therefore, we need the strength of acids. The strong bases, well, they missed that here. We need to include the strong bases. And the stability of certain ion combinations, precipitation, and gas formation, precipitation and gas formation. Now, use these ideas to predict the favored direction of each equilibrium given. In each case, state whether you expect the equilibrium concentration to be large or small. So anyway, this is a kind of a tricky one here. But basically here we're going from sulfurous acid to water and sulfur dioxide. So which one do you expect? Well, they're calling sulfur dioxide aqueous. I called it a gas. Sulfur dioxide is normally a gas, so some of this will come off, but it's polar. It means it has a bent geometry, and so, or gas. So we say gas formation is one driving force, but another driving force is going from a stronger acid to a weaker acid. sulfurous acid to sulfur dioxide, the stronger acid to weaker acid. But this is one I asked you to memorize, you know. I asked you to memorize 3.
Professor?
Yes?
It's break time.
Okay, we'll take a break. Carbonic acid was 1. Oh, let's take a break now. So we'll start up again, about 15. Thanks for the reminder, Catherine. So what I was saying is about the other thing is, you know, you start thinking about you know, once you start off memorizing, then you start thinking about things more deeply, and then start thinking about connections, you know, for why, you know, why certain things are the way they are. And so that's good. Like here, you'd see H2O is liquid. And so automatically you've seen, okay, there's a difference between liquid and gas. So then you're on the lookout for that. And so H2O is liquid here. So that wouldn't be included in the K. But as far as driving forces go, driving forces is, you know, which direction do you expect to be favored? You know, do you expect the driving force to be forward, that is downhill forward, or do you expect the driving force to be reversed, that is the downhill directions reverse? Again, we're just looking at energy in terms of that. And so first you memorize the basics. Then pretty soon you start thinking, you know, okay, why is it stronger acid, weaker acid? You know, why is that? Well, it kind of makes sense. Stronger acid is more reactive, weaker acid is less reactive. But then you can start making additional connections. You know, why precipitate? Why gas formation? Why, you know? And then as you start thinking about these things, then more connections can come. And one of the connections is this. There's another way of thinking about these. These driving forces, and one way of thinking about it is going from a stronger electrolyte to a weaker electrolyte. That's another driving force that we see as well. And so here, you know, if we don't have the acid chart, you know, for example, is SO2 really a weaker acid, stronger to weaker? Because SO2 is also an acidic acid. This is a Lewis acid. And do we have the Lewis acid chart, and how do I position it, you know, in that context? So this one is a question mark here. And so there are other things we could fall back on. And one thing is that weak acids are weak electrolytes. They partially ionize in water. However, this is not, you know, weak electrolytes are weak acids, weak bases, and some heavy metal salts. So H2O liquid's a non-electrolyte, and SO2 is a non-electrolyte. And so in that context, we expect this to be favored in the forward direction because we're going from a stronger electrolyte, even though this is weak. I wouldn't label this a strong electrolyte. I wouldn't label this a strong acid. It's a stronger acid. It's a stronger weak acid than this. But am I sure? Because this is not on the chart. I'm just guessing. You know, and this they wrote as aqueous, not gas. If this were gas, then that would be easy. Well, no, why gas? Well, gas, there are reasons for that, you know. But those reasons you think about, you know, the first step, if you have all the reasons, maybe sometimes that makes it easier, you know, to memorize. Other times it's just too much. You know, you just want to get the basics memorized first and then start thinking at the more advanced level. Sometimes the explanations are quite complex. And so anyway, for sure we could see we're going from a stronger electrolyte, although this is a weak electrolyte, to a weaker electrolyte. These are non-electrolytes. And so this is going to be favored in the forward direction. And so this is, you know, although in the context of this question, it might be tricky because you have to make that connection. And when you read the question itself, you know, here, read the question. In chapter 9, we discussed how to identify major and minor species. You know, how many people even remember chapter 9? You know, I'll tell you a lot don't. You'd be surprised. You know, a lot of students, they're just, everything's short-term memory, crammed. Nothing long-term. And so if you remember from chapter 9, well, we can always go back. You know, this is an open book. We can always go back and read it. We discussed how to identify major and minor species and how to write net ionic equations. These skills are based on the solubility of ionic compounds, the strength of acids, and the stability of certain ion combinations. Use these ideas to predict the favored direction. Now, how the heck am I supposed to use this idea? You know, how's this connected to chapter 9? And so this would be an example of a higher level, you know, because they aren't telling you exactly how to use this, you know, and so you have to make the connection yourself. And yeah, that not only happens here, but it happens, you know, like I might have told you this before, but I found practically every single test I took at UCLA, like 90% was just stuff that was talked about. It's just, okay, if you remember it, you got it. But 10% was a little bit more, you know, a little bit more like here, a new connection, you know, new connection is made. Can you figure it out? You know, that kind of thing. And so 10% was what we call challenge, you know, challenge. But you can get these challenge problems if you have the basics down a lot better. So that's a utility, you know, again, I know there's a big push against memorization, but I think memorization is so, it can't be emphasized. It's so important in building knowledge. Okay, so here we're going from a stronger electrolyte to a weaker electrolyte. So that's our driving force. And weaker electrolytes, why? Why do weak electrolytes break apart? Well, it's because their bonds are strong. And so if we're going from weaker bonds to stronger bonds, then that's indicating that we're forming something more stable. And so these types of things you build up on, you know, you build up a little bit at a time. It's not all crammed in at once, but you build up a little bit. And this is why that repetition, you build up these things, you know, so by the 10th time you go through it, it's not just memorizing it. It's, you know, you're beyond the memorizing part. You're looking at it at a deeper level to try to understand things at a deeper level. The equilibrium is favored in the forward direction. H2SO3 is one of the acids that is unstable, decomposing. Okay, so this is just straight memorization. H2SO3, you memorized it as being unstable, but then why is it unstable, you know, and other things. K is large for this equilibrium. And so this is one of the ones that you should have memorized. There are 3 of them that I gave you to memorize. Carbonic acid, sulfurous acid, and ammonium hydroxide are unstable in metathesis reactions. Okay, here we're going from H plus and acetate to acetic acid. This one's fairly straightforward because H plus or hydronium is a stronger acid. Acetic acid is a weaker acid. And so here we're going from a stronger, more reactive acid, H plus or hydronium, to a weaker acid. Now, where does the H plus come from? The H plus can come from different sources. Like, for example, we could add some HCl and sodium acetate. If we mix HCl and sodium acetate together, this is the reaction we'd expect. It's the net ionic reaction we'd expect. And so acetic acid is weak acid. Nearly all the ions will combine to form the molecule. All right. Well, that answer. You know, the other way of thinking about it is we're going from these strong, you know, this would be a strongly electrolytic solution, the ions, to something that's a lot less. You know, it depends on the source of the ions. This particular reaction we'll see in the reverse. This is called ionization. Acetic acid partially ionizes in water, or hydrolyzes in water. This is what causes the pH. You know, pH of acetic acid is due to acetic acid colliding with water to form hydronium in acetate. And we can measure that hydronium. The hydronium is going to contribute to the water's hydronium, which is going to make the water solution acidic. 1810. Cobalt-2 hydroxide dissolves in water to the extent of 3.7 times 10 minus 6 moles per liter. Find its KSP. KSP, I didn't do KSP calculations here. I skipped them. KSP you'll do in Chem 1B, but KSP we can get, how do we determine Ks? A lot of Ks are determined empirically. And so what they do is they take some cobalt hydroxide and then just try to saturate a water solution with it. And so if we were trying to figure out what the K, the ratio is, the equilibrium constant ratio for this particular process. So we'll take some cobalt hydroxide, solid, and then just try to dissolve it and saturate the water. X with ions. And so this is going to form cobalt ions and 2 hydroxides. So initially a little bit of this will dissolve and the concentration of the ions will increase. Once the concentration of ions hit a certain point, then they'll precipitate at the same rate that they're dissolving, and we'll reach a state of dynamic equilibrium here. Now we want to figure out the ratio, and so the ratio is the product, and so this would be the cobalt-2 concentration times the hydroxide ion concentration here, squared. Now this is a pure solid, and so this is divided by 1. So we usually leave that off. This is divided by 1. We don't really include that. And so what we need is we need to know what the concentration is of the saturated solution. And so initially we start off with nothing in there. And so it's 0 molar and 0 molar. And then there's a change. The change will build up, and so we're going to increase it. And so this is going to be what we call plus S molar plus 2S molar until we hit a saturation limit. At the saturation limit, we're just going to have S molar and 2S molar. And so for every S that I get, I'm going to get twice as much hydroxide when this dissolves. And so I don't know what that S is, but I can measure it. And so we can go ahead and measure what S is using some technique like titration. For example, we could figure out what the concentration of hydroxide in there is via titration. Once we figure out the concentration of hydroxide, then we can figure out the concentration of cobalt, because cobalt would be half as concentrated. And then we plug that in here, and then we can solve for K. And so what they did was they figured out the concentration of cobalt. This is the concentration of cobalt. And if we have the concentration of cobalt, then we double that to get the concentration of hydroxide. So the concentration of hydroxide would be twice as much, 7.4 times 10 minus 6 molar per liter. S is called the solubility. And that's the extent to which cobalt. For every cobalt that dissolves, 1 cobalt-2 hydroxide dissolved. And so that's how much cobalt-2 hydroxide dissolves. And then we just plug it in. We plug it into the equation, we can get what the K ratio is. So let's figure out the K. So here, this K is called SP, which stands for solubility product. And, so that's why they have SP here. So they figure out the cobalt concentration is 3.7 times 10 minus 6. Therefore, the hydroxide is double that, 7.4 times 10 minus 6. And then we plug it in here, 3.7 times 10 minus 6 for the cobalt, and then the hydroxide, 7.4 times 10 minus 6 squared, gives us 2.0 times 10 minus 16. It's not very soluble. It's not very soluble because it's a very small number. It's mostly this, very little of this. There's very little ion product. Ion product would be cobalt ion times the hydroxide ion. That's the ion product. There's very little ion product there, so very little ions went into solution. And so that's an example of determining K for empirically. This is empirical determination K. We can also determine K, the ratio, theoretically using thermodynamics, which is done in Chem 1B, not in Chem 4. Even though these aren't required, I skipped them. You could just look at them. For example, if 2.50 times 10 squared, 250 milliliters of water dissolved only 8.7 milligrams of silver carbonate, what is KSP? So this tells us, how much dissolved. And so for every silver carbonate that dissolves, we form 2 silvers and 1 carbonate. And so this is the concentration. This will be the concentration of the carbonate here, because every silver carbonate will form 2 silvers, 1 carbonate. So here we get the molarity of the silver carbonate. And the molarity of the silver carbonate is equal to the concentration of carbonate because 1 carbonate forms for every silver carbonate. So we get that molar. Silver concentration is double that. So that's the concentration. Then we plug it in here and we can get the ratio. Again, the ratio is very small, telling me silver carbonate's not very soluble. Find the moles per liter and grams per 100 milliliters solubility of silver. Okay, this is just going backwards. You know, here we figured out, you know, how much dissolved and then figured out K. Here they're giving us K and wanting us to go backwards. And so how do we go backwards? Well, from the KSP, we get the equation here. It's going to be silver times iodate. And silver concentration equal to iodate concentration, which we'll call S squared. And so we set this up in a table, but it's just going backwards here. And this KSP stuff is beyond the scope of the class. You know. Find the solubility, this is going backwards again. Find the grams, this is going backwards again. Figuring out how much dissolves. Yeah. Okay, this is something called Ka. Ka we also skipped, and this is the pH of this acid here, you know, 0.22 molar. And the acid, how the acid changes the pH is acids will form, let's see, they're using H+, so I'm going to use H+ too. What happens is, you know, weak acids are weak electrolytes, and weak electrolytes partially hydrolyze in water or partially ionize in water. And so if I have this acid like this, C4H5O3, what happens is a little bit of this will break apart, you know, to form H+ and C4H5O3 minus. And this H+ here will cause pH. So they're saying the pH is 0.22 molar. The pH is 2.22 molar. This is at equilibrium, you know. Then we could figure out the H+ concentration. The H+ concentration is 10 to the minus pH molar. Once we figure out the H+ concentration, the H+ concentration should be the same as this anion concentration. And so once we have these two concentrations, then K is just actually these are all aqueous. K is the H+ concentration, which we can solve from the pH, and then times this concentration. This concentration we can solve based on this, because for every H+ we get 1. It's a 1-to-1-to-1 mole ratio, divided by this acid concentration. This one we need to set up a table for this one, is best. But this is called Ka. Ka, acid ionization constant. It's the acid ionization constant. And here we can get the percent ionization depending on how much, you know, ionizes. Is it 99% this and 1% that? Then it would be 1% ionization. The calculations, again, this is optional, so I'm skipping them, but I just want to briefly look at these here. You know, the types of things that you can do here. Here I'd set up an ice table, though. They're not doing it the easiest way. You know, there's an easier way of doing this. Find the pH. So this is just working backwards. So if we're given the Ka, we should be able to find the pH. If we're given the pH, we should be able to find the K, you know, the ratio. You know, the K, how much H+ generates depends on how much reaction we have, you know, how much product we get. And so it's going to depend on the product to reactant ratio. Here, a student dissolves 24 grams of sodium acetate. Sodium acetate's a base. In 500 milliliters, there are 500 milliliters of 0.12 molar acetic acid. Find the pH. All right, this one is a bit more complex, this problem. This one, let's see if they used the ice table for this. No, they didn't. I'm going to skip this one entirely. This is what we call a buffer. This is a buffer problem, and for buffers, we could set up. We should set up using an ice table. There's an easier way of dealing with it. This is also a buffer. There's a buffer. Buffers are interesting solutions. You know, a buffer is like acetic acid and acetate are solutions in which you have a base coexisting with an acid. Normally when we think about an acid and base, the acid and base should attack one another and react and neutralize each other. But if both are weak, if you have a weak acid and a weak base, then they can coexist. You know, they'll react a little bit, but they won't react completely because they're not strong enough to react completely. And so there's more of a coexistence if both are weak. If one is strong and the other's weak, then the reaction goes completely. It's like Chem 4 style stoichiometry. And so it's just when both are weak. When both are weak, it forms a somewhat stable mixture of weak acid and weak base. So this is kind of an interesting solution because it's both an acid and a base. Usually it's biased towards one. So for example, acetic acid, acetate, which is acid and base, is biased towards the acid because the pH is a little lower than 7. So the acid's stronger than the base, but it's still a mixture of an acid and base. Buffers are very important, of course, in biology. You know, biological systems, you'll have the CO2, carbonic, you know, acid buffer system. And the phosphate is also another one, dihydrogen phosphate and monohydrogen phosphate. It's another buffer, but we're skipping buffers. So buffers, the interesting thing about buffer solutions is they're very resistant to being attacked, you know. Like for example, buffers, you can attack them with both acids and bases and they'll resist those pH changes. Like your blood is very well buffered. The pH of your blood is like 7.2. If the pH of your blood goes to 7.4 or 7.1, you know, or 7.0, you're in big trouble. And the pH can change dramatically, you know, with added acids or added bases. And so the pH of your blood has to be stabilized, and then there are lots of things trying to change the pH of your blood, and so it's got to be buffered to resist those changes. Otherwise, you can't sustain life. A scientist introduced 0.351 moles of carbon monoxide and 1.340 moles of chlorine into a reaction chamber having a volume of 3.00 liters. When equilibrium is reached according to the equation here, there are 1.050 moles of chlorine. So this is determining K empirically, again, from experimental data. And what we can do is we can see what the change is. You know, here we start off with initial, and then we see what the change is. And from that change, we can figure out all the equilibrium concentrations here. And once we get all the equilibrium concentrations, we can get K. So that's what they're doing. They're setting up an ice table here. So we start off with this initial, and then they're telling us how much it changed by giving us what it is at the end. We convert all these into concentrations because K's the ratio of concentrations. And so that's why the numbers don't look the same, because they got to do concentration. And they got to calculate the concentration carbon monoxide, concentration chlorine at the start, and then they calculate the concentration chlorine at the end. So if we know that, then we can fill out the rest of the table. Filling out the rest of the table, then we can get the equilibrium concentrations. When we get the equilibrium concentrations, we can determine the K. The K value here is 14, which means it's pretty even. You know, we're going to get pretty much close to a 50-50 mix, you know, of product and reactants here, kind of thing. It's 14, just slightly biased here, but you know, the numbers are different. So this is filling out the table. And so filling out the table, what they did was they gave us some information. What was given here in the table? What was given is this was a given, this was a given, this was a given, and this was a given. Everything else was derived based on this. And it was derived based on, you know, we got to lose some of the carbon monoxide. But whatever amount of carbon monoxide we lose, which we call X, we have to lose the same amount of chlorine. And so if I have this, then I can figure out what X is, because 0.447 minus X has got to be 0.350, and therefore X is 0.097. If X is 0.097, then that means this is the same at 0.097, which means this is the same because whatever we lose here, it's a 1 to 1 to 1 mole ratio. So this is going to be plus 0.097 over here. And so, and then we can figure it out because this minus this gives us this, this minus this gives us this, and this plus this gives us this. And then once we have all these equilibrium concentrations, then we can just plug it in here. And so this is a standard equilibrium stoichiometry calculation. Equilibrium stoichiometry calculation. It's different than our standard stoichiometry. Our standard stoichiometry, we figure out what the limiting reagent is. You know, it's a 1-to-1. This would be the limiting reagent. The limiting reagent is consumed. So the limiting reagents would go to 0. And then we have the excess reagent. And this would be our theoretical yield. You know, this is totally different because we don't completely consume anything here. This equilibrium, there's some left over. You know. How much is left over depends. And this is determined empirically from experiment. And so it's a general chemistry again type problem. Now the math for these can get horrendously difficult. The math for these, this math is easy here. But the math can get a lot harder. The reason the math can get a lot harder is because the coefficients here. This one is particularly easy because the coefficients are all 1. But let's say you threw a 6 in there. If you threw a 6 in there, then it's a 6th order equation. And sometimes, well, they didn't show it. Let me see if they show it. Sometimes the changes, this one, the math is fairly easy, but other ones, you know, what you're solving for is a lot harder to determine, and you need to solve higher order equations. True or false? Some equilibria depend on a steady state of reactant. That's false, you know. We don't, a steady supply, no, everything's fixed and nothing's changing, so this is false. Both forward and reverse reactions continue after equilibrium is reached. Yes, that's true. This is the dynamic part of equilibrium. Every time reactant molecules collide, there's a reaction. That's false. We need energy and orientation. Potential energy during a collision is greater than potential energy before or after the collision. Yeah, that's true here, you know. Potential energy, because what you're doing is you're making what that transition state, that transitory state is very unstable. That transitory state is where you're breaking bonds and forming bonds. That's true. The properties of a transition state are between those of the reactants and products. That's true. That's false. Well, in a way, it's true because you're breaking bonds and forming bonds, so it's between, you know, it's like partial bonds. But in another way, they're right. It's false because the chemical properties are going to be quite different. If you're just looking at the bonding properties, this would be true. If you're looking at chemical and physical properties, if you could, in theory, isolate this is not stable. But if you could isolate it, then it would be false. Activation energy is positive for both the forward and reverse reactions. That's true. It's got to climb a hill either way you go. Kinetic energy has changed potential energy during collision. Yeah, I didn't really talk about this. Kinetic energy is motion. And so if you have some physics, then this is discussed in great detail, the dynamic between kinetic and potential. If you're on a swing and you're out here horizontally, you're maxed out in potential energy. You might not be moving. Let's say this is at the top of the swing. And so you're not moving for a moment. And so this is max potential energy. You have potential to move quite fast, and you do. When you hit the bottom of the swing, then you've maxed the kinetic energy. Then you go up the other side, so you're slowing down, so kinetic energy is going down, but you're going up, so the potential energy is going up. until you max out here. And then once again, you maxed out the potential energy and zeroed the kinetic energy. Well, that's the same thing with a transition state, you know. You got the kinetic energy and you got to go up the hill. Once you hit the top of the hill, you've maxed out the potential energy, and the kinetic energy, it's just stopped. It's either going to fall down to the left or fall down to the right. And so an increase, this is true. An increase in temperature speeds the forward reaction but slows the reverse reaction. That's false. It speeds up both reactions. A catalyst changes the steps by which a reaction is completed. The steps we call a mechanism. Yes, that's true. An increase in concentration of a substance on the right-hand side of the equation speeds up the reverse reaction rate. That's true. The more product we have, the more reverse reaction will occur. An increase in the concentration of a substance in equilibrium increases the reaction rate in which the substance is a product. That's false. Increase in concentrated substance is going to favor the opposite reaction. Reducing the volume of gaseous equilibrium shifts the equilibrium in the direction of fewer gaseous molecules. That's true. Side with less gas. Raising temperature results in a shift in the forward direction of an endothermic reaction. Yeah, endothermic reactions consume heat, so raising the temperature is going to favor that. The value of an equilibrium constant depends on temperature. This is true. The ratio changes with temperature. We can see one important ratio is Kw. It's extremely important, Kw. Kw is extremely important because that dictates water. For pure water and solutions, Kw holds regardless. And so in pure waters and in solutions, so I could add salts, I could add acids, I could add bases to this, and Kw is always going to hold as long as the temperature is 25 degrees C. This is a Kw at 25 degrees C. Now, if I increase the temperature, Kw increases because I'm going to have more collisions. I'm going to generate more hydronium, more hydroxide. And so at higher temperatures, I'm going to have greater than 10 to the minus 7 molar. Well, if I have greater than 10 to the minus 7 molar, that changes my pH. That's absolutely right. Your pH is going to change depending on the temperature. Therefore, pH meters, modern pH meters will compensate, you know, because the hydronium ion concentration will increase at higher temperatures and decrease at lower temperatures. Well, that changes the pH because at 25, it's pH 7. At greater than 25, we're going to be at lower pHs. At less than 25, we're going to be at higher pHs because the concentration is fluctuating. To prevent you from going crazy, what modern pH meters have is a temperature correction. And so what it does is it just takes pure water, and regardless of the temperature, it always keeps pH 7. And so even though the pH actually does change, if you have just a sample of pure water and the temperature is fluctuating, the pure water will stay pH 7. Otherwise, you're going to go crazy with those temperature changes. And so, or, you know, if you have an older, we used to have older pH meters with a little knob, and the little knob, you set the temperature. So you measure the temperature and then you set the temperature of the pH meter. And so regardless, pure water is going to register pH 7, you know, regardless of the temperature. And we just offset everything that way. A little more, that's more Chem 1A stuff, or Chem 1B. Large K indicates that the equilibrium is favored in the reverse. That's false. Large K favors the product, forward reaction. At time 1, two molecules are about to collide. At time 2, they're in the process of colliding, and their form is that of a transition state. Compare the sum of their kinetic energies at time 1 with the kinetic energy of the transition state at time 2. You know, the kinetic energy of the transition state, we freeze the transition state. You know, it's at the top. And so it's like the swing. the kinetic energy should be 0 at time 2. The kinetic energies are greater at time 1 and because at time 2, the kinetic energies have been converted into potential energy. In other words, they slam together, bonds are breaking. We need to break the bonds. And so the kinetic energy is transferred into potential energy, breaking the bonds. List 3 things that you might do to increase the rate of the reverse reaction. Actually, there's no answer for this one, so skip that. Just doing the ones that you could review quickly yourself, you know, in your studies. You know, that way you have more details in this. So when you do review it, you can hopefully get more out of the review. It says this is short, you know, this is a quick 6 weeks. Like, you know, I'm not sure how you guys felt, but I felt that the 6 weeks was it was really short, you know. You don't have that much time to review, unfortunately. Compared to regular semesters, regular semester is 16 weeks. Our semesters used to go on 18 weeks. You know, when I first started El Camino, there were 18 weeks and went down to 16 weeks, a lot shorter. Quarter systems, 10 weeks. And so here UC, except for Berkeley, UC Berkeley is still in semesters. But if you're at UCLA, you know, quarter system is 10 weeks plus the final exam, and so technically that's 11 weeks long. And so, you know, quarters go by quick too. Usually, since they go by so fast, people start ahead. You know, a lot of people get a head start. You know, all the people I knew, all the people I knew got a head start. They were studying, you know, before the first day of class even hit, so they wouldn't fall behind. You know, everybody's just trying to, because this is 10 weeks is so fast. Yeah, everybody's just trying to get a head start so that when, you know, you get hit with a lot of assignments due at the same time, you don't fall too far behind so that you can still catch up. Anyway, the Haber process for making ammonia by direct combination of the elements is described by the equation N2 plus 3H2 yields 2NH3 plus 92 kilojoules. If a manufacturer wants to make the greatest amount of ammonia in the least time, removing product as the reaction proceeds, is the manufacturer more likely to conduct the reaction at high pressure or low pressure? And so, what do you think? High pressure or low pressure is better for this one? Yeah, that's correct. That's good, Anthony. Low. Oh, actually, low pressure. No, wait a minute. Low pressure is going to favor the, well, one way of thinking about low pressure is bigger volume. And so if you have bigger volume, then we're going to favor the side with more moles of gas. If we have smaller volume, which we'd get from high pressure, we're going to favor the side with fewer moles of gas. So it's actually high pressure to force the reaction to the smaller number of gaseous product molecules. You know, you don't, it's good, you know, in science, people aren't afraid to, you know, one of the ways you learn things is, you know, you just try it, and if it's wrong, you know, you learn from mistakes as well. Sometimes mistakes are the most memorable learning experiences when you make mistakes. This is why peer review and referee, you know, sometimes you'll make a mistake and hopefully the reviewer or the referee, they call them referees, if you're publishing a paper, could catch it. You know, sometimes you miss it yourself. And so this is why peer review is so important in science. High temperature or low temperature? This one. Okay, high temperature. Okay, so the way you can think of it is we're adding heat. If we add heat, heat is a product. So if we add heat, then we're getting a lot more product. If we're getting a lot more product, then if this is at equilibrium, it's going to shift it to the left. And if we remove heat, then we're moving product, and then that should shift it to the right. And so that's one way. The other way of thinking, this is always the way I think of it, because I've been, you know, sometimes you try to think about things in different ways and more memorable ways. But the way I always think about it is this. Ice, you know, adding heat favors making ice or melting ice. And so when I think about ice and water, I think of the formation of ice as exothermic. In other words, in order to make ice, you need to remove heat. And that's what the job of the freezer is to remove heat. And so when you make ice, you remove heat. And so if you want to make more ice, you remove more heat, lower the temperature. And so making ice is exothermic. Melting ice is endothermic. If you want to melt ice, you add heat. And so I always remember this. I always remember that melting ice is endothermic, and increasing temperature favors melting ice. And so increasing temperature favors the endothermic direction. Well, this is exothermic. This is exothermic, so this is like making ice. And so adding heat or increasing the temperature here is not going to favor the forward because this is exothermic. Increasing the temperature favors the endothermic direction, which is the reverse direction. This is not written, this is written in Chem 4 style. In Chem 1A, we'd never write it like that. In Chem 1A, it's written like this. Delta H is equal to minus 92 kilojoules. That tells me it's exothermic. So if it's exothermic in the forward, then that's like ice, making ice. Making ice is exothermic. We want low temperature. So low temperature is going to favor making ice, which is exothermic. This is exothermic, same thing. Whereas melting ice is endothermic. And so if this were positive, then I'd want to add heat to do that. And so this one turns out to be low temperature. Oops. This one would be low temperature. They're doing two things here. And I must have misread this. In the least amount of time. Okay, this is it. So there are two things that are fighting each other here. One thing that's fighting each other is this. Okay. This is an exothermic reaction. So exothermic reactions are favored at lower temperature. However, if you decrease the temperature, that means the collisions are slower. And the collisions are slower, then we have a problem. And so what they're doing is they're sacrificing some yield. What they're saying is, okay, they have enough. Like, for example, when I was doing the reactions yesterday, I said, okay, I have enough precipitate. I'm not going to wait for it to complete because it's taking too long. And so I have enough. So what they're doing is they're sacrificing some yield for speed here. And so, of course, at higher temperature, you're going to get faster collisions, and that's going to result in more energetic collisions, which is going to increase the rate. And so it's going to increase the rate of production, but it's going to decrease the yield. And so what they're asking for is just the rate here, what increases the rate. And so they should have just said that. This is going to increase the rate for both the forward reaction and the reverse reaction. And so if it increases the rate for both, and then it's going to skew. When we change the temperature, it changes the ratio here. And so it's going to skew this. And so in this one, because of the more complex nature of temperature in this particular problem, they should have just said which one's going to result in a faster rate of reaction, regardless, forward or reverse, would be higher temperature. Okay, so you're right, I was wrong in this context here. Okay, under proper conditions, the reaction in question 83 will reach equilibrium. Is the manufacturer likely to conduct the reaction under those conditions, that is at equilibrium? No. If they're trying to make this stuff, they want to maximize the amount of ammonia here. And so there are different ways you can maximize the amount of ammonia. One, you could lower the temperature, which will increase the ratio here. The other is you can remove the ammonia. As ammonia is being formed, you remove it, and that results in a Le Chatelier shift. So you want to continually be removing the ammonia. Okay. The reaction in question 83 has a yield about 98% at 200 degrees C and 1,000 atmospheres. Commercially, the reaction is performed at about 500 degrees C and 350 atmospheres, conditions at which the yield is only about 30%. So here they're sacrificing the yield to get a faster reaction, you know, and so they're increasing it from 200 to 500, but then the amount of product is going down, but they say, well, it's okay, that's enough product. They just want it to go fast. Okay, let's take a break here well, it's going to be a little bit early break, but let's take a break here for 15 minutes, sorry. And then we'll resume after that. I have to take care of one thing. Thanks.